Thank you for showing up tonight. My name's Steve Manlove. I'm a psychiatrist. You might, do psychiatrists think about health? Well, sometimes they do, and I do. Maybe it's, I trained as an internist while I was training as a psychiatrist, and I always kind of wondered about the connection between what was going on in the body and the brain, the heart and the brain, that sort of thing. I really didn't connect it to my practice or what I was doing in my general psychiatric practice until sort of late in life. And I was doing a new kind of procedure called transcranial magnetic stimulation. And I began to realize that people who were responding to transcranial magnetic stimulation seemed to be people who were more actively engaged in lifestyle changes too. And began to wonder if there was a connection there, and began to do a deep dig into brain physiology and how it was affected by lifestyle, and began to work with people on lifestyle issues while we were also treating their depression. And actually, Mandy, back in the back there, is the main person who does our lifestyle work with transcranial magnetic stimulation now. So this is a brain. And it looks like kind of a big blob, right? But it's really quite complex and much more than a big blob. The lower part is the temporal lobe. The top left, which is, this brain is facing toward me. The top left is the frontal lobe. The middle part of the brain is the parietal lobe. The back is the occipital lobe, and underneath it is the cerebellum. And you can see there's a line kind of right in the middle of it. That is a fissure. To the left of that is a motor strip. That's where that part controls all of your motor activities. To the right of that is the somatosensory strip that is where all the sensations get kind of processed. And where the temporal lobe kind of connects with the frontal lobe, right above that is a Broca's area, which is the speech part of the brain. So there's lots to this, and what I want to do in the first part of this talk is just kind of talk about how the brain works, the physiology of it. I think if you understand that, then then why we are making these changes or suggesting these lifestyle changes will make more sense. A couple of interesting facts. Your brain is the fattest organ in your body and may consist of at least 60% fat. Your brain consists of about 100 billion neurons. There are anywhere from 1,000 to 10,000 synapses for each neuron. So there's lots of synapses, lots of connections between neurons that are running through this mostly fatty organ. There are 100,000 miles of blood vessels in your brain, obviously very small. The brain is bathed in cerebral spinal fluid. And information is primarily transferred in the brain by neurons. And neurons are both electrical and chemical kinds of cells. So both of those things are going on in the neurons. We're going to talk some more about that. So how do neurons work? So neurons have specialized projections. Neurons are brain cells. They have specialized projections called dendrites and axons. Dendrites bring information to the cell body, and axons take information away from the cell body. Information from one neuron flows to another neuron across what's called a synapse. It's a little space between the neurons. And this is a cartoon of a neuron, and I just kind of shows you some of those landmarks I just mentioned. You can see the dendrites, that's what bring information into the cell. And this cell body is the thing that's around the nucleus there. And then the axon goes to the right and goes to axon terminals. I want to talk about stem cells briefly here. You all have heard about stem cells. You've heard of stem cell transplants when people have leukemia and that sort of thing. Neurons are made from stem cells, as all cells in the body are. They're all made from stem cells. And stem cells are undifferentiated biological cells that can differentiate into specialized cells. Stem cells, when I was in medical school, I thought that there were no new cells being made in the brain. That was what we were taught. We now know that there are stem cells in the brain and that they can create new cells. They were identified in the hippocampus and the olfactory bulb several years ago. And now there's evidence that there are stem cells in other parts of the brain as well, which is really an exciting idea, because you can actually repair your brain, and the brain actually does repair itself if given the right situation. This is a picture of two neurons back to back. Starting at the left, you can see dendrites, kind of like that other picture. And they go into the cell body, and then that triggers an action potential, which is a electrical impulse that goes down to the end of the axon. And at the end of the axon, there's a synapse that connects that to the next cell. And so that synapse is a little small space that it's really important, because it's both filled with different kinds of molecules and hormones and stuff like that. It also is the medium that neurotransmitters go across to get from one cell to the other to communicate in the chemical way that cells communicate with each other. There's this process in the brain that's called synaptoblastic, synapse forming, versus synaptoclastic, synapse destroying behavior. And the brain is continuously dynamic in that sense. It is, if you were to look at a small slide of your brain, you'd see these synapses forming and being destroyed continuously, faster than you could even look at it. As we're sitting here talking, your brain is working the synapses, and that's a big part of neuroplasticity. Is that synaptoblastic, synaptoclastic dynamic. This is another picture of two neurons next to each other, and it just kind of highlights that the synapse between the two bigger areas there. And you can see again, there's the axon goes to the end of one cell, the one on the left and on the top. And when it gets there, when the action potential gets there, it stimulates the release of neurotransmitters that go across the synapse to the other cell. So you can see each of these pieces of the brain are really important. The axon is important, the transduction down the axon is important, but also how this synapse works and how these billions of synapses work is really crucial for brain dynamism. And this is just a little bit bigger picture of the same thing, where you can see an axon terminal, there's a space in between, and there's a dendrite on the other end, and it's communicating by sending neurotransmitters across that synapse. And the one thing that this doesn't show is all of the milieu inside the synapse. Again, it's things like hormones, metabolic factors, minerals, vitamins, things like that are all kind of in that milieu. And the richer that milieu is, the better the synapse conducts the neurotransmitters across it. So one of the questions that I began to ask when I was thinking about how do we make the brain more dynamic and possibly then more treatable, that was my theory, was to ask, how can we improve the functionality of the synapse? How can we make that so it just cruises right across and stimulates the receptor on the other side really well? So this next, I'm going to kind of synopsize some of the things we just talked about. There's a concept called neuroplasticity. Plasticity means adaptability. It means changing. So neuroplasticity is brain changing, adapting the synaptoblastic activity, all the things that are going on in the brain to keep it dynamic and plastic, changing. So neuroplasticity, the ability of the brain to reorganize itself and create new circuits in response to our environment, and remarkably, actually, in response to our own thoughts sometimes. We now know that there is the potential for lifelong plasticity in the brain. In recent decades, we've discovered that the brain is plastic throughout our lives. And then there's a potential for new neuron growth. Recent research has shown that there's stem cells, as we talked about a few minutes ago. So neuroplasticity, to have the best neuroplasticity in the brain, it requires, number one, the ability to generate new neurons from stem cells. How do we set this up so that the stem cells can adapt into neuronal cells? Second, the ability for dendrites to grow and create new synapses. So there's this continuous process of dendritic growth too. Remember those dendrites, on the one end of the cells, they are growing and creating new synapses. So both growing and creating synapses. Third, the proper balance between production and destruction of synapses, that's the synaptoclastic versus synaptoblastic activity. And then finally, optimal synaptic function. How do we make that milieu in that synapse as dynamic and as able to make the neurotransmitters go across it as possible? So this is one of my favorite slides, neuroplasticity over time, and I want to show you this picture. It's really super important, not just for adults, but also for children and how we think about children. These are tissue slides that are turned into pictures. So these are brain tissues, and we see that in a newborn, on the far left, there are the dots, the little black spots are cells, and the lines are axons between these cells and dendrites. And you can see that there aren't that many in the newborn, right? And then in 1 month, look, there's probably over twice as many. And then by 9 months, it's beginning to be quite complex, right? And finally, at 2 years, it's just a big tangle of nerve cells and dendrites and axons all mixed up. And so this is what is going on in an infant's brain, and it speaks to the importance of enhancing neuroplasticity in infants. We want them to have a dynamic brain, to have lots of growth. The stem cells are most active in infants, and that's why they make so many new cells. And we know that works better when children are brought up in a supportive, loving, calm environment. And so it makes child development and how we think about it really important, because if we don't provide our children with that, they don't have nearly the growth that you see. And actually, I did a case that I was doing in Albuquerque a few years ago, where I was dealing with a child who'd been neglected and abused, who is now 14 years old. And we did some studies on him using, sophisticated brain imaging tools, and found that I wasn't really looking for this. I was looking for a brain injury, but the readout, the report by the radiologist said, well, his frontal lobes are 20% smaller than the average child who's 14. And I said, well, why is that? And the neurologist said, oh yeah, well, this is a well-known phenomenon that children who grow up in neglectful, abusive homes have decreased frontal lobe development. So you can actually measure that, and things hadn't gone that well for this 14-year-old kid. Then at around, as an adult, you see that there aren't quite as many cells, but and the axons and dendrites are a little bit darker. And that's what is happening during adolescence is the tracts are getting myelinized and they're getting thicker, and there's a little bit of pruning of the cells so that that is organizes people's thinking and allows connectivity between different parts of the brain in better ways. And it starts in the back of the brain, moves to the front by about age 25 is when that process of myelination and making these tracts is completed. So I don't know. I thought that was a nice visual to kind of look at what's generally happening. So again, this is that naked brain, but kind of giving you some idea about what's going on in different areas. The frontal lobe is the conductor. It manages things, executive functioning. It's under development until people are 24 years old. I just today testified at a hearing in Pure about how we sentence people who are 18 to 21 because the brain isn't fully developed. So should that change how we think about sentencing people in that age group? The temporal lobes are on the bottom there. That's connected to the hippocampus and the amygdala, long-term memory and emotional centers of the brain. The cerebellum's on the bottom, supports higher learning, math, music, advanced social skills. The occipital lobe is where the vision is processed. So it goes from your eyes through the middle of your brain to the occipital lobe, and that's where it's processed. Then the parietal lobe is kind of a numbers, sensory input, allows people to learn to be analytical. So a few fun facts, just to ease up the stress here. The average number of neurons in the human brain, 100 billion. I mean, it's a lot. So more than in an octopus, right? 300 million. And the rate of growth during development of a fetus while in the womb is 250,000 neurons per minute. So again, think about not just early childhood development, but intrauterine development of the human brain and how important that is. So we've talked about how do we keep the brain dynamic? Well, there are a lot of neurodegenerative disorders. I'm not going to go through all these, so don't worry. But I just point this out that there are lots of neurodegenerative kinds of disorders. What is most important is that the most common one is Alzheimer's disease. The second most common one is Parkinson's disease. So these are both illnesses that everybody is somewhat familiar with. And then multiple sclerosis and Huntington's disease are the other two that are more common. The other bunch, there's quite a few of them, are pretty uncommon actually. And I want to share a hypothesis that neurodegenerative disorders are really caused by poor neuroplasticity, and we could decrease these neurodegenerative disorders if we could enhance neuroplasticity. And then how do we do that? So I saw a person with Parkinson's disease today, and I'm thinking, okay, there's standard treatments for Parkinson's disease, but I also want to working with this person on enhancing neuroplasticity because he's got a degenerative disease of the brain. And with Parkinson's disease, the cells that make dopamine become atrophic or depleted. So if we could improve his neuroplasticity, maybe you could at least decrease the rate of that problem developing. So I want to, we've talked about neurodegenerative disorders, and I gave you a big list, but I want to kind of point out, and this is a simplistic slide, but cognitive disorders, Alzheimer's disease are a big one, but depression is actually a disease of neuroplasticity also. And why is that? Well, if you look at brains of people who are depressed, you see that parts of their brain have atrophy, and you can actually see this on like PET scans and functional MRI scans. And you can see that if you treat it, that atrophy improves. It becomes more normalized. So my point here really is that not only should we be thinking about neuroplasticity with diseases like Alzheimer's disease, but we should be thinking about it with diseases like depression and anxiety and psychiatric illnesses also. So with cognitive decline, we see shrinking of the hippocampus, and it's a normal process. You can see there's a bunch of neuropsych testing results, and you can see that over time, it's age on the bottom, and between age 20 and 80s, the scores in a lot of these neuropsych testing on the average go down. They slowly decrease. You can see that. But there's some that don't, right? The ones that don't are world knowledge. And those stay fairly flat until the late 80s. Then they, on the average, go down. But so there's a natural loss of some cognitive function as people get older. And can we reduce that by improving neuroplasticity? My bet is yes. And we're going to talk more about that. So this is a picture of a slice through the brain, like going right through where my hand goes through, right? Kind of horizontally through my brain. And you can see the hippocampus, those two little, look like J's in the middle of the brain. And you can see that the hippocampus looks like a seahorse, right? And does anybody know what hippos means in Greek? Horse, yeah. And do you know what campus means? So, no, we're stretching here. It means monster. Yeah. So it's, a horse monster. It looks like a seahorse. That was, there was a lot of mythology about seahorses as being monsters, evil entities. But so that's how the hippocampus got its name, was because when they pulled it out, it looked like a seahorse. So what causes cognitive decline? Don't we all want to know that? So the neuronal death in the hippocampus causes a decrease in the size of the hippocampus and overall brain size, but the hippocampus goes faster than the rest of the brain. And it's associated with lower scores on memory tests. If you look at a hippocampus, if you look at my hippocampus and compared it to the average person, if it were smaller, I would very likely have poorer memory scores than people with a bigger hippocampus. So it sort of suggests that you want to keep your hippocampus as big as possible, right? But with aging, the hippocampus atrophies faster than the rest of the brain. It shrinks by about 0.5% per year after age 40. So by the time you're 50, it's shrunk 5% on the average. By the time you're 60, it shrunk 10%. By the time you're 80, it shrunk 20% on the average. So are there things that we can do to decrease that process, right? And that's why we bring in this concept of neuroplasticity. Are there things that we can do to decrease the rate of decline of our hippocampus and other parts of our brain? So I mentioned before, depression is due to atrophy, and it's due to atrophy of an area right under my hand here called the dorsolateral prefrontal cortex. And that's actually when we see that, that was part of the reason why this treatment that we use called transcranial magnetic stimulation that we use to treat depression, it stimulates that part of the brain that is atrophied. And when it's successful, that part of the brain is no longer atrophied. It comes back to normal. So the cells are not dead. They're just atrophied. Follow me? we're trying to get them active again. And I'll show you what we are doing there. This is 3 different looks at a cell, dendrites, and axons. So you can see that the cell body is kind of in the middle on the bottom ones. It's in brown. The axon goes down in all 3 of these. The dendrites go up, right? And you can see, looking at these bottom 3 pictures, that there are more dendrites on the left and more on the right than there are in the middle, right? And that's because when people get depressed, they have fewer dendrites. But not only that, if you look at the top are cutouts of dendrites and that are magnified. So look at the one on the far left. You can see dendritic knobs are those little white bumps that are coming out of the dendrite. And the axons are connecting to those knobs and making synapses, right? And that's what it looks normally, about roughly that number of dendritic bumps or bulbs. When you're depressed, you can see there are many fewer of those, so there's much less capacity to make a synapse. And there's fewer dendrites, there's fewer synaptic or dendritic bulbs. And when it's treated, for instance, when we treat it with transcranial magnetic stimulation, but anytime a depression gets better, what is really happening is you're getting more of those bulbs on the dendrites and more synaptic activity, more synaptoplasticity, and that sort of thing. There's a variety of ways that we do that, but that is what the goal is to increase dynamism of the brain, increase dendritic growth, increase the capacity for synaptic activity, those sorts of things. So now I want to talk with you about how do you improve neuroplasticity. I'm going to give you a copy of this sheet. I'm going to spend a little bit of time going through each of these steps. And these are, in my mind, simple steps that take very little effort, take some, but things that people can do to improve their neuroplasticity. And it's my bet that this will make your brain less likely to have typical neurodegenerative diseases of the brain. First, change lifestyle habits. You already know these things already because smoking and alcohol intake affect lots of parts of your body, but they definitely affect your brain too. As you know, alcohol is a neurotoxin. Smoking causes vascular disease. That those 100,000 miles of blood vessels in your brain get plaques on them and don't work well when they get clotted up. So smoking and alcohol are pretty much, we all know that. But why? Let's just take a look. These are 2 brains. The one on the left is an older person, 80-year-old person who did not drink. The one on the right is an 80-year-old person who was a heavy drinker. I don't know if you can see the difference, but there's the gaps between parts of the brain are much, much bigger. And that's because the brain has atrophied. It has shrunk, and it's left those gaps in between parts of the brain. So if you ever wondered if alcohol causes brain damage, this should put that to rest. The second idea is to engage in aerobic activities. So my general suggestion is try to do 30 to 60 minutes, 4 to 6 days per week. The more, the better, basically. If you have a hard time getting started, what I always talk to people about, and one of our tricks is to say, commit to exercising for 1 minute a day, because and give yourself permission to stop after 1 minute if you want to. But almost everybody who exercises 1 minute will continue to exercise for a longer period of time. It's getting started that is hard for people. Aerobic exercise like walking, biking, running, swimming, anything that makes you sustain an elevated heart rate is important. But when you elevate your heart rate, it's possible that you could exacerbate cardiovascular disease. So you should just be sure that you don't have a problem waiting to happen there. But it's also true that anaerobic exercise and weights and resistance training can help the brain too. And why does this happen? I mean, as I mentioned earlier, when we first started doing this transcranial magnetic stimulation, we noticed that people who were exercising seemed to do better. It was just a serendipitous observation. But I took a deep dive into exercise physiology, and one of the things that exercise does better than almost anything is it increases a hormone in your brain called brain-derived neurotrophic factor, BDNF, as it's noted up here. And BDNF, brain-derived neurotrophic factor, means brain-derived from your brain. Neuron, trophic means growth. So it literally makes your brain grow. Enhances brain growth and therefore neuroplasticity. And this just kind of shows the process that leads to this release of BDNF. So exercise causes ketone formation in the liver, especially if you become mildly ketotic from exercising. That's partly why the long distance exercise can be helpful. The ketones cross the blood-brain barrier, and they cause gene activation. And when that gene is activated, it causes the release of BDNF, brain-derived neurotrophic factor, in your brain, and that makes you smarter, and it makes your whole brain function better. BDNF also induces cholesterol synthesis that is required for synapse development. So it increases that capacity for synaptoblastic, synaptoclastic activity that I've talked before as part of neuroplasticity. The third rule is minimize consumption of processed sugar. Natural sugars in fruits, vegetables, unsweetened dairy products seem to be better, but you want to avoid like granulated sugar, high fructose corn syrup, honey, maple syrup, even juice, because fruit juices are very highly concentrated sugar sources. So what about this? Well, okay, you know that increased blood sugar triggers the release of insulin, right? But if you don't know that, that's what happens. It causes your pancreas to release insulin, so that the insulin makes the blood sugar go into your cells. High sugar consumption, then, when you get above a certain amount, it results in what's called a hyperinsulinemic state, an elevated insulin state. And chronic hyperinsulinemia, which is essentially what type 2 diabetes is. Type 2 diabetes is the disease that's characterized by chronic hyperinsulinemia. The elevated blood sugar and the hyperinsulinemia is toxic to the brain. So why is that? So one reason is that there's an enzyme that breaks down insulin that's called insulin-degrading enzyme. That enzyme, insulin-degrading enzyme, also breaks down amyloid. And amyloid is the substance involved in plaque formation in Alzheimer's disease. So if there's so much insulin and you're trying to break it, and you're using up all of the insulin-degrading enzyme to break down the insulin, you don't have enough left to do the normal cleaning of the brain by breaking down amyloid. And that's at least one reason that chronic hyperinsulinemia causes brain illness. There was just a study out within the past month that looked at people with Alzheimer's disease and people with metabolic syndrome, which is part of type 2 diabetes and hyperinsulinemia. And it showed that people of the same age with the same, who had metabolic syndrome had roughly the same amount of brain atrophy as people of that age with Alzheimer's disease. So we know that hyperinsulinemia and metabolic syndrome causes brain atrophy. The incidence of dementia is twice the rate in people with metabolic syndrome than it is in the general population. So you can imagine with the incidence of metabolic syndrome in our culture that we're seeing lots of brain problems just related to that. Recently, it's been found that there's a lot of insulin receptors in the hippocampus, and we're beginning to sort out what does that mean, because that's, of course, the part of the brain that does memory, right? And is there some dynamic there also? The fourth rule is to minimize consumption of grain products, especially processed wheat. So there's some evidence that wheat and sugars together increase inflammation throughout the body, including the brain. So minimizing wheat and sugar intake can help you lose weight, in addition to improving neuroplasticity. Concentrated sugars in wheat cause a spike in blood sugar, causes a spike in insulin, and we've talked about insulin causing a decrease in neuroplasticity. The hint here is if you need a snack, don't eat sugar. Don't eat the cookie that's sitting in your break room, like I'm always tempted to do. Eat a piece of fruit or some nuts or something like that that doesn't cause the blood sugar spike that sugar alone would give. There's a book written about this by a guy named David Perlmutter. It's called Grain Brain, but he goes through all the scientific background for why grain itself is a problem. I'm going to just talk to you a little bit about that. So we all create something called zonulin in the intestine when you take in gluten, and gluten is in wheat, right? So this protein, gluten, found in wheat, barley, and rye, makes our gut more permeable, and it's triggered by it triggers this zonulin, and what happens is you want your gut to be somewhat permeable, to have sort of like little holes in it that nutritionist stuff can get into your body through, right? I mean, that's, you're absorbing things from your GI system, minerals, sugar, vitamins, and stuff like that. But if those spaces between the cells are too big, then bigger things get through, bigger proteins that are also in your GI system. And your body's not used to that. It doesn't really know what to do with them. It notices that there's something different in there, and it views them as an antigen, which means something that is a foreign body in your body, and so it makes antibodies to those things. And there's a theory that a lot of the huge inflammatory illness process that we have going on in our medical world today is related to these too big proteins getting into your blood system and then developing an immune response to them. And then that immune response also attacks parts of your body, and you get arthritis or other autoimmune diseases. So if you decrease the gluten, you decrease the zonulin, you decrease the size of those pores, or it's not really pores, but spaces between cells, and you have less of these bad proteins that trigger inflammation getting into your body. The fifth one is sleep. Try to sleep around 8 hours a night. Not always so easy to do, but a good goal. If you have trouble sleeping, looks like melatonin 0.5 to 3 milligrams is a pretty safe thing to do. It does look like other sleep aids probably cause dementia. It would be a good thing to not use them if you don't have to. Things like benzodiazepines and stuff like that. It's a debated issue, but I think today the balance of the literature suggests that maybe they're more likely to cause dementia than to be dementia protective. So it's probably not a good way to get sleep. Sleep apnea is a very common problem, and I just mentioned that here because that's a huge percentage of the population, and that can be treated pretty easily. It's worth checking that out if you snore or if your bed partner notices that you don't always breathe regularly. So sleep is, why sleep? What does sleep do? It's brain cleansing time. This was sort of a comment that I hear a lot when I talk to people about sleep. You know that awesome feeling when you get into bed, fall right to sleep, stay asleep all night, and wake up feeling refreshed? Well, me neither. So what happens in sleep that is good for your brain? Well, in the rest of the body, there's a lymphatic system. That is a way that when we have an infection, the lymphatic system takes over and gets rid of waste in your body. It kind of parallels the vascular system. The brain doesn't have a lymph system, but it does have a lymphatic system. And this lymphatic area is made by brain cells that hollow out, in a sense, space in the brain. And this is kind of a complicated slide, but what I really want to, I think the take-home message here is that there's a pretty good evidence now that when you sleep, the vein in this slide that is taking blood away from the brain, this lymphatic system that surrounds that vein opens up and allows waste products to get into that vein and take them out of your brain and takes them somewhere, takes them to your kidneys and liver and where you can metabolize them and get rid of them. So sleep it really allows your brain to sort of flush out the toxins. And the brain is making using lots of energy and creating lots of waste products. And we need to get rid of those in some way, and there's not another way to get rid of them. That is how we get rid of them. There's no lymph system to do it. There's not a kidney or a liver in your brain that metabolizes them. They only get out of your brain by being drained out through this lymphatic system into veins, and then processed by the rest of the body. It's also, there's a big correlation between headaches and sleep, and possibly, at least the current theory is that if you don't clean your brain with good sleep, you are more likely to get headaches. I've had that experience myself if I don't sleep, and I did an experiment on myself for 27 years doing call every third or fourth night and not sleeping, and I routinely had headaches after call. Which, when I read this about headaches and the lymphatic system, I thought, I'm living proof. The headache stopped the day I stopped doing call, and the day I started sleeping at night. Yeah, so there's a phenomena called sleep toxicity that, and I don't know the biology of it, but people who sleep excessive amounts, and it varies a little bit from person to person. If you sleep excessive amounts, people tend to be less clear and sharp in their thinking. Then it looks like there's some sort of magic about roughly 6 to 8 hours that makes people feel the best afterwards. The sixth is kind of a no-brainer in my mind. Take vitamin D3. We know at the latitude we live at, we just, especially in the winter, cannot make enough vitamin D because we don't have enough sunlight exposure. Most of us really aren't even outside during the winter too, because it's cold and stuff. So there's very little downside to taking 2,000 units a day of vitamin D3. Maybe you need less in the summer, and you can do vitamin D blood levels and find out exactly how deficient you are. But I've checked several hundred people vitamin D levels, at least several hundred, and in our latitude, unless they're taking they're vitamin D deficient. And why is that important? Vitamin D it's a cofactor in lots of chemical reactions that are going on intracellularly. It reduces inflammation, reduces autoimmunity, improves brain function, reduces cancer cell growth in studies, improves immunity, enhances mood and sleep, reduces the risk of heart disease. And there's a big study in Germany where they were looking at something else, but they happened to check vitamin D levels as part of the study. And they found that people who had vitamin D levels in the high normal range, not just in the normal range, but in the high, above the 50% line of normal, had a dramatic reduction in infections, cancer, and lots of sort of immunity-related problems. I thought that was, I personally took vitamin D, and one day I checked my blood level, and it was close to 100, and I thought, well, what kind of damage am I doing to myself? So I did some research on that, and I concluded that I probably didn't need to be that high, but it was more likely helping than hurting, keeping it in the high normal range. I'm not going to do this slide, it's too confusing. The seventh thing to consider is to take omega-3 fatty acids, like fish oil, right? Start low, aim for 2,000 milligrams twice a day. Most capsules have around 1,000 milligrams in them. So there are two kinds of omega-3 fatty acids in fish oil. One is called EPA, the other is DHA. The higher the EPA, the better for your brain. Start with one capsule in the morning, go up to 2,000 milligrams twice a day over the course of a week. Otherwise, you might, some people get kind of a upset stomach or a fishy taste in their mouth. So why? What is the reason for this? Why might omega-3s be helpful? Well, for starters, remember that your cells, all through your body, but also in your brain, the cell walls are made up of lipids, which are like omega-3 fatty acids. So you are giving yourself building blocks for cell walls when you do this. Also, just statistically, if you look at people who take omega-3 fatty acids as a higher percentage of their fat intake, they have a bigger hippocampus than people who don't. So if you value the size of your hippocampus, which I think you should, this might be helpful. Number 8 is fast 12 hours each day. So I try to fast between dinner and middle of the morning. I try to get in something like 12 hours or more. I found it fairly easy for me personally to fast between dinner, say 7 o'clock and 10 or 11 in the morning. So that's actually like 14 or 15 hours. After that, I start getting, I don't feel like I'm thinking quite as clearly, but it varies from person to person. A lot of people will fast really from 6 p.m. to 2 p.m. But why? How might that help you? We can imagine that if you're fasting, you're not taking in glucose, or anything that could be broken into glucose. So you're not triggering insulin release, right? Glucose triggers insulin release. So you are giving your body the chance to not use insulin-degrading enzyme to break down insulin, but to clean your brain. Kind of track that. And it also, in addition to that, if you fast, and it depends on each person how long they go before they become ketotic. And you remember that picture of the guy exercising and it made his liver produce ketones? Well, anytime you produce ketones, you are triggering the release of brain-derived neurotrophic factor, which is the magic hormone that makes your brain grow. So fasting is sort of like exercise in that sense. They both trigger ketone formation in your liver and thus cause brain-derived neurotrophic factor to go up, makes your brain grow. Now, I thought this was an interesting quote. Science is always looking for the magic bullet. However, we already have the capability within us. Fasting is a magic shield. It protects healthy cells while the unhealthy ones self-destruct. And that's talking about a phenomena, I'm going to connect here in just a minute. Number 2 here, called autophagy. So when you fast and you are no longer using your food, the sugar in your body to give you energy, there's a process called autophagy, which means that your body actually breaks down old, no good cells and devours them, cleans them out, and allows your body to create new cells that are better and more functional. So the benefits of fasting are autophagy by inducing ketosis, which I just mentioned, but also keeping your insulin level from spiking before bedtime, because an insulin spike at that time seems to contribute to insulin resistance, inhibition of melatonin, and inhibition of growth hormone. So these hormones are all interconnected. And it's not that easy to do, but as Teddy Roosevelt said, nothing in the world is worth having or worth doing unless it means effort, pain, difficulty. What a typical TR quote. I've never in my life envied a human being who led an easy life. I've envied a great many people who led difficult lives and led them well. So fast, even though it's hard. And then the last of these suggestions is to challenge your brain. Meditative experiences, intellectually challenging experiences, music, all are helpful because they cause your brain to have to create new synaptic connections and improve. It triggers a need for neuroplasticity. So this is just a meditating person, and music, is something that you can learn and you can keep doing all of your life, and learn it even as an adult. And those are the simple answers to what you can do to improve your brain health. This is just mentioning that I'm going to do another talk. It's not we haven't advertised it yet, but it's a follow-up to this talk, which is really about how can you prevent dementia and treat dementia. We don't have any medicines that help it. So what can we do? And these are sort of the foundation, but there's more also. Anyway, thank you for listening. Thoughts? Yeah. I think whole wheat is better, but because it's got the whole grains, because they give you more fiber, and fiber can decrease the absorption of insulin. It decreases the absorption of blood sugar, of glucose. So, well, I mean, there's lots. When you eat vegetables, I mean that's what. Well, you can make it on lettuce. Yeah, no, I mean, I'm not, this is, the TR quote, right? I mean, it's not easy because these are things that we've all done all of our life, and I get it. I mean, it's better. Well, I'm not saying, okay, I think I understand that it could be a message that is a message you could take out of here. That's really not what I'm trying to say. I'm trying to say we should reduce these things and not make them staples for us. And make it, and try to slowly back off of it and try to eat things that are better for us, like unprocessed foods and vegetables and clean meat and fish, because fish have omega-3 fatty acids. I know stopping eating sugar, I'm like the worst, but I mean, I try to, just reduce it. I no longer sit down and eat a pack of cookies in one sitting, and I try to, do all kinds of little games in my mind to not expose myself to them, because if they're there, I want them. I mean, me and everybody else in the United States is addicted to sugar, but it's a problem. And in my mind, one of the games that I play with myself is to say, well, I'm thinking of sugar as poison, because it actually is. And I might want to have some poison once in a while, but probably not too much, because I'd like to live a long, healthy life. Other thoughts or ideas? Yeah. Yeah, right. Mm-hmm. Yeah, interesting. So I don't know for sure, but in this particular situation, I happened to follow this kid for many years. And he was reading at a second grade level when he was 14, which may suggest something about his frontal lobes. That's the part of the brain that learns to read and manage words. He was put into a residential treatment facility that had a good education system and had tutoring, and was in a very active learning environment. And by the time he was 18, he was reading at college level. And when I heard that, I thought, we got to do that test again and see how big his frontal lobes are, right? But I couldn't do it. It was a test that cost about $20,000. So it was a very complex thing to do. But it did make me think that there's a chance that people in the right environment, if they're given the right, probably food and nurturing and educational experience, might have an opportunity to actually grow their brain. So, yeah. It was an interesting, I was very curious about that when he was 14. Where will this kid, what will he look like when he's 18? I happened to see him again then, and he was in many ways much more functional. But he was certainly cognitively much more functional. Well,
I always said we had two sons, teenagers, and I had said this about every teenager, and even myself. You should never judge a person by their teenage years. And so when you said that, it's like, yeah.
Yeah, well, the argument from a developmental perspective is that the frontal lobes, which are what manage impulses, connect with the middle of the brain and tell it to, don't do what your impulse is to do. The frontal lobe is not fully developed until very late. It's the back of the brain myelinates and develops the connections first. And so a 18-year-old may be a fabulous baseball player, but don't ask them to make good judgments about social situations or managing their impulses or executive level functioning because the front of their brain isn't fully developed yet. It's a tough art. It's a tough discussion to have because I understand there are some people who feel that it should be justice by reciprocity. In other words, if you did the crime, then do the time. But the truth is the brain is not developed when you're 21, and it does develop after that. And almost all violent crimes occur between 18 and 25, and almost always in males, of course. After that, most violent, there's still some, but if you look at a graph, I can show you a slide right now, but just huge peak at that, actually about 19 or 20, and then it goes down.
Study of the brain. That would be a big help.
Well, of course. Yeah. Yeah. And there is a lot being done. It's a fun time in brain research. Yeah, we do there's a way of treating depression that's called transcranial magnetic stimulation. And what it does is it uses electromagnetic waves that you can create with the figure of 8 coil, so it's sort of like a figure of 8. In the middle of it will cause an electromagnetic beam that will go to a conducting surface beneath it, whether that's an axon in a neuron or a copper wire, and it can cause conduction if you pulse that. And this transcranial magnetic stimulation we use to pulse that part of the brain that I mentioned is atrophied in depression, and triggers an electric pulse down the axon, and it appears that by doing that makes the brain develop more plasticity and regrow and no longer be atrophied, and then treats depression very well.